Okay, you guys, here we're talking about the big triangle proportionality theorem, which is kind of silly because it's just a bunch of little algebraic shortcuts and things like that, but it is really useful, okay? So it's review slash it's a big idea, okay? So here we have, if we have this case where we have a triangle and then this parallel line passing through it, we already knew, like just using past information, right? We know that corresponding angles are congruent, so these match, plus in both the big triangle and the small triangle, they both have this angle A at the top. So really, the triangles are similar by AA, right? And so I just drew them here. And so what we know is that the sides AB over here is proportional to, and I can't say it's equal, but I don't know, I'll put like a wavy one arc, right? These are similar. And then also the sides on the right, so AE, wavy, is proportional to, well, it's kind of a cool, I like that. It's proportional to AD. So symbolically, we know those were already the case. All right, well, the new theorem says, well, actually, we could take this a step further and just say this part is proportional to this part. We don't need to just say, up in the last one, it was only that this part is proportional to the whole side, the same as this part is proportional to the whole side. That was from similar triangles. But with a little algebraic trick, we could say, well, actually, these two segments ratio is the same as these two segments ratio. And so let's just algebraically look at the y there. And then the converse is true also. So down below, well, we go, okay, well, from just past information, we knew in this triangle that this triangle was similar to the big triangle. What are the side lengths? Of the little one, it's A and C. And they have this angle, and it's all lined up, right? Here's the 2 from corresponding. Here's the angle it had. Here's the 1. Here's the 2 from corresponding. So this whole side length here was A plus B. And over here it was C plus D. And so what we already had, just from they're similar by AA. So they're proportional. So A is to A plus B. A is the same ratio as C is to C plus D. Okay, well then we could just solve for this. So cross multiply, so we get A times C plus D is the same as C times A plus B. Okay, well let's solve this a little bit. We get AC plus AD equals AC plus BC. So I just wrote them alphabetically. But look at this, we have the same AC on both sides. So let's subtract AC and we get AD equals BC. Well, could we write this as a fraction? Well, look at what we want. We want the A and the C on top. So let's just divide both sides of this by the B and the D. So if we divide both sides by BD, right, we can do that as long as neither side is 0. We can do that. And what we're left with then is that cancels and we get A over B on this side. And on the right, the B's cancel and we're left with C over D. Well, that's exactly what we wanted. A is to B, these two segments, is the same ratio as C is to D over here. What? So if the lines are parallel, those segments in one triangle are proportional. That's cool. Okay, well, what about on the right? What if we start with that? We just work that same thing in reverse. We say, well, what if we start with this proportion? Well, we could cross multiply. So that's AD equals BC. And then, just like we subtracted the AC earlier, for no apparent reason, just because we're clever, we're just going to add AC to both sides here. So we have AC plus AD equals AC plus BC. And if we hadn't just worked the forward, you'd be like, why? Who would think to add AC? And then we just factor out the A here, times C plus D, equals, and then we factor out the C here, A plus B. And then again, we go, well, we want to get the proportionality of the big triangle. So we want to show that A is to A plus B is the same ratio C is to C plus D. Okay, so let's do that really quick. Okay, so if we started with that ratio up at the top here, we're just algebraically, now we're going to divide by A plus B times C plus D on both sides, and we'll divide over here A plus B, C plus D. And what happens is the A plus B's cancel, the C plus D's cancel, and what we're left with is A is to A plus B, same ratio as C is to C plus D. And what does that mean? Well, they share an angle and their sides are similar. So if they share an angle and their sides around that angle are proportional, then triangles similar by SAS, right? Triangle similarity. And so what does that mean? If the triangles are similar, well, then their angles are the same. And if the angles are the same, then corresponding angles congruent means parallel. So up here our theorem just says, if we have parallel lines there, then this ratio, right, the segments of the sides are cut proportionally. And then, same thing, if we have a line that passes through our triangle, that was a rough line passing through our triangle, but if a line passes through and cuts the two sides into the same proportions, well then that line is parallel to the third side. That's the idea. So it's a biconditional. If a line passes through, right, so you have a triangle, and if you cut a line through that's parallel, that cuts it into these are proportioned the same way as these are proportioned. Okay, that's the big idea. Very cool. Well, it's got a lot of consequences. Really, this mid-segment one is just a little tiny corollary of that, just a little addition, right? So we define the mid-segment of a triangle just to be connecting the midpoints of two sides. So every triangle has multiple, right? So if I have the midpoint of this side, the midpoint of this side, and they're all different midpoints, right? We're not assuming any of these lengths are the same. So we cut these three different sides in half, and if I just connect those, I get one mid-segment, two mid-segments, three mid-segments. All right, so there we go. They're all mid-segments, three different ones. That's what it looks like when you cut it up. So that's what a mid-segment is. Well, look at this. The mid-segment obviously cuts these sides proportionally. Here's A and A. Here's B and B. What's the ratio of A to A? And what's the ratio of B to B? That's 1 equals 1. So just by what we just did, if those ratios match, then the side is parallel. So great, it's parallel. And what's the ratio then? Well, this is exactly like compare the two triangles, right? I'm reasoning it out here, right? So if this is A, this is A, if this is B, and then this is B. So A is to A as B is to B, question mark? Yeah, 1 equals 1. So since those are proportional, then by the triangle or the converse of the triangle proportionality theorem that we just did up there, so if those ratios match, then lines parallel, okay? And so if lines are parallel, what that means is we have all these angles that are the same corresponding. So then we have triangles similar, right? And look at the ratio of the similar triangles, right? Here's the similar triangle, similar to this one. Here's A and 2A, B and 2B. So what's the ratio? It's a 1 to 2 ratio. There's no like magic here. And so the mid-segment theorem says, if you connect the mid-segment of the two sides, then that mid-segment is parallel to the third side, and it's half the length. So if this is C, this is 2C, right? Just like this top one is A, and this whole length is 2A. And this length is B right here in the small triangle, and in the big triangle, it's 2B. Yeah, so there's no magic there. Again, it's just similar triangles by AA. It's the triangle proportionality theorem up above. Okay, shoo, cool corollaries to this. And then we have even another corollary. Okay, well, what if we just have a bunch of parallel lines? Just a bunch, like 4, 5, 10. And they cut two different segments. So these two green lines are two random transversals. And 4 parallel lines cut them. Well, then all of these are proportional. So A is to D, as B is to E, as C is to F, or vice versa. You could write that proportion as A is to B, as D is to E, and B is to C, as E is to F. So these are proportional. Now, again, the Y is just the one same theorem, right? Well, why are they proportional? It's just because, look, you just make these connect, and boom, it's a triangle now. Let's call this like X and Y. Well, we go just from the last theorem. If we're talking about this triangle right here, well then, X is to A as Y is to D. And then we do the same thing. We go, oh, well, what if actually this was the triangle, and we were talking about these two parallel lines here? Oh, well, then we go, well, X plus A is to B as Y plus D is to E, and then we could just algebra that thing, and we just keep doing that sort of thing, and we end up getting that these are proportional to these are proportional to these, and it's just a consequence of that same triangle proportionality theorem. So it all comes down to the fact that if you have a parallel line in a triangle, it's creating two similar triangles. That's it. And with a cool algebra trick, then we know the two segments it cuts are proportional on both sides. So A is to B as C is to D, or A is to C as B is to D. Right, that's the big idea. Parallel line through your triangle cuts it proportionally, and so the sides are cut proportionally. That's it. And we just use it over and over, okay? Now here's a really common mistake though. Really common. All right, so when you have this parallel line cutting through, you can use all these shortcuts, but still fall back on the key, which is corresponding angles means that we have a 5, 6, 7 triangle similar to a big triangle that's 15, right? The whole left side here is 10 plus 5, and then the whole right side, y plus 7, and then the whole bottom, x. Now there's no problems. Now you just set up your ratios. You go, oh, well, this triangle is really just 3 times larger. So that means I could do, whoops, I just switched pen to the exact same color. So that means this is times 3, this is 18. And this one is times 3, so this is 21. And so that means y is 14, right? So that's one way to do it, right? But when you draw it out like this, there's less mistakes. Here's the common mistake, right? People go, oh, look, this is a 1 to 2 ratio. 5 is to 10 as y is to, or 7 is to y, right? That's true. That's the proportionality theorem we just did above. 5 is to 10 as 7 is to y. So that's, we can just see it's 14 already, but cross multiply, we get 5y equals 70. We divide by 5, we get y equals 14. Great. Now the problem is though, is people incorrectly, I'll do it in the color of the title. People go, 5 is to 10 as 6 is to x. That is not what the triangle proportionality theorem is. These are entire side lengths of the triangle, and so those entire side lengths are proportional to entire side lengths. So you could correctly say, over here on these right diagrams, you could say 5 is to 15 as 6 is to x. But the key common mistake people often make is they use this segment. They say portion is to portion as portion of side is to portion. Correct. But then they use it for this third side. That third side did not get cut proportionally by the parallel line. That is not what the triangle proportionality theorem says. So that third side is the common mistake. And that's why I actually don't use the triangle proportionality theorem that much. Instead, almost always, I just redraw the two triangles and I add up. I say on the left, oh, the big triangle had a whole side length of 15 and a whole side length of 7y and a whole side length of x. And now I forget that original picture and I just go to this, and there's way less mistakes now. Now it's just side to side is side to side. Everything's similar by AA. It's straightforward, right? But that's super common mistake. For example, if we just use the triangle proportionality theorem with that like mid-segment special one, look at this. So if I connect the midpoint of the sides, let's say this triangle was, I don't know, like 6 on this side and 10 on this side. Well, the mid-segment theorem, if I use the midpoints of both sides, that means I have a 3 and a 3 and a 5 and a 5. And so whatever length I pick here for the bottom, let's say this was 6. Does that mean this is 6? No! You can visually see it is getting wider as it goes down, right? We could calculate this pretty easily. Naturally, the theorem up above says if you connect the mid-segment, it's half of the length of the other. But the reason is because this is 3 is to whole side 6, 1 to 2 ratio. 5 is to whole side 10, 1 to 2 ratio, as 6 is to whole side 12, right? And that's why drawing it separate as 3, 5, 6 is similar to 6, 10, and then putting like an X here. There's way less mistakes than if you try and reason out. It's super common here that people will say, oh, this bottom one is 6 because 3 is equal to 3, 5 is equal to 5, so 6 must be equal to 6. And that's a super common mistake, and it's totally understandable. Okay, let's just do a bunch of homework problems now. So find the length of the missing side. So here we just use the triangle proportionality theorem. It's not the booby trap where it's asking for the parallel sides. It's the common just straightforward. So let's call this x, and we go x is to 3 as 12 is to 4. And so I'll just actually simplify this on the right. That's a 3 over 1. So x over 3 equals 3 over 1. So cross multiplying, we get 1x is 9. Right? Over here, let's put this as a y. And so now I could again go side to side in the same direction, but instead I'm going to go this way for no reason. So we got 14 is to y as 12 is to 18. Again, as long as you're going in the same direction and not like switching backwards, that's okay. All right, so 14 is to y, and then I'm going to simplify the one on the right. Dividing by 6, I get 2 over 3. So I get 14 over y equals 2 over 3. Cross multiplying, I get 2y equals 42. Dividing, I get y is 21. Okay, straightforward. Now this one's saying, now are the lines parallel? Now remember the triangle proportionality theorem. Whoa, I just moved that. I didn't mean to. Remember the triangle proportionality theorem is biconditional. So the converse is true. If those sides are proportional, then the lines are parallel. So it's just asking us to do the same problem in reverse. It's saying check the proportion and if proportional. So let's do it. So this is to this. So 8 is to 5 as 12 is to 7.5. Now again, this is a question. We don't know that this is true, so we're going to check it. Well, on the right, I'm going to multiply top and bottom by 2. So that's actually 24 over 15. Then I can divide by 3, and so that becomes 8 over 5. Oh yeah, 8 over 5 does equal 8 over 5. Check. So yes, parallel. All right, and explain. It's by the converse of, so this is by converse of Triangle Proportionality Theorem. Okay, next one, let's try. I'm going to do a different order. Let's do in the same direction this way. So 18 is to 24. Question mark equal to 10 over 15. So dividing by 6, I get 3 over 4. Is question mark equal to, dividing by 5, 2 over 1. No, not the same. So no, not parallel. So sad. Okay, next one. Find x and ed if, so we got some variables here. So we got 3 for AE, we got 2 for AB, we got BC is 6, and ED is 2x minus 3. So again, because of this parallel, triangle proportionality theorem tells us 3 is to 2x minus 3. So the segments on this side are in the same ratio as the segments on this side. So I went from the small top one to the bigger bottom. So same thing. 2 is to 6. So then on the right, I'm going to reduce that to be 1/3. So I get 3 over 2x minus 3 equals 1/3. Cross multiplying, 1 times 2x minus 3 equals 3 times 3. So adding the 3, I get 2x is 12. I get x is 6. Let's plug it back in because it asks us to find ED. So times by 6, we get 12 minus 3. We get 9. Okay, so x was 6. ED was 9. All right, and that makes sense because 3 times 2 is this. 3 times 3 is 9. So that worked out. Okay, find all these measurements if. Ooh, and it gives us some crazy ones here. So it says this is 6, AF is 8, BC is X, CD is Y, DE is 2Y minus 3, and FE is X plus 10/3. Let's see what we can do. Well, first, I could use, because of these parallels, I could use the triangle proportionality theorem here. So I could say 6 is to X as 8 is to X plus 10/3, right? Now we can solve for X, so let's cross multiply. 6 times X plus 10/3 equals 8 times X. So distributing 6X plus, so if I multiply 6 by 10/3, that's 6 over 1. These cancel and give me a 2 there, so that's equal to 20. And then I get 8X. So subtracting the 6X, I get this, and X equals 10. All right, so I could plug that back in. So I get erasing now. I get 6 and 10. And over here, I get 10 plus 10/3. So 10 plus 10/3 is equal to 30 thirds plus 10 thirds, so that's 40 thirds. Okay, so now we're going to use it the other direction, okay? We don't know a lot about parallelograms yet, but if we did, we could say opposite sides are the same, so this is 10, this is y. Maybe that would be useful another time, but who knows, okay? So we don't know that yet. That's for chapter 8. All right, so let's get rid of this, move some. So now we're going to use triangle proportionality theorem the other way. So we have these two lines are parallel, so that means these sides are cut proportionally. So the ratio of 40 thirds to 8 is the same as 2y minus 3 is to y. So cross multiplying, we get 40 thirds y equals 8 times the total 2y minus 3, that is a group. So I'm going to multiply both sides by 3 really quick, get rid of that thirds. So I have 40y equals 24, 2y minus 3. Okay, I don't distribute because this is only one term. This is item times item. Just like if I had 2 times 3 times 4, I would just go, that's 6 times 4 is 24. I wouldn't go distribute that in, that's 6 times 8. That's not the way multiplication works in one term. The only time you distribute is when you have your distribute into parentheses where there's one term plus or minus another term, just to be clear. All right, so anyways, distributing, we get 40y equals 48y minus, and that's 60, 72. So subtracting, we get negative 8y equals negative 72. Dividing by negative 8, we get y is 9. Okay, let's plug it back in. We get 18 minus 3 is 15 here. Okay, so let's erase this. And then plugging it back in here, we get 9. Okay, and we can double check these ratios. So 9 is to 15, so that's 5 thirds. And if we multiply this by 5 thirds, we get 40 thirds. So yep, check. I just did it in my head really quick, but you could write it out or use a calculator. All right, so this one, oh, look at what they did. Now they're having us use the mid-segment theorem. So we know we're connecting the midpoint of this side with the midpoint of this side. That tells us these are parallel. Tells us the triangles are similar. Well, first, the obvious one is these are shown to be congruent, right? It's the midpoint just given to us. So 3y minus 9 equals 2y plus 6. So subtracting, we get 1y left on this side. Adding the 9 is 15. So plugging in, we get 30 plus 6, that's 36. And over here, we get 45 minus 9, that's 36. Okay, so that worked out. And then, again, the common mistake here would be to say that x plus 2 equals 5 thirds x plus 11, right? But that's not true. They're not the same. If you separate these triangles, you have the big triangle is similar to the little triangle, where you have a half of the side and the full side, so it's in a 1-to-2 ratio, right? Or another way to look at it is, this is 36, and this is 36 plus 36, or 72, right? So either way you look at it, it's a 1-to-2 ratio, or you use the theorem, which says the mid-segment is parallel to the base and and half its length. So we know that this x plus 2 is equal to, I'm going to erase this. We know that x plus 2 is half as long as 5 thirds x plus 11. That's the expression we get. Or you could write it in reverse and say, and say 2 times the mid-segment equals the longer one there. So I am going to multiply both sides by 2. So I get 2 times x plus 2 equals, and now the half is gone, 5 thirds x plus 11. So that's 2x plus 4 equals 5 thirds x plus 11. I'm going to now multiply by 3 on both sides because I don't want that fraction. So I get 6x plus 12 equals 5x plus 33. Subtracting x, I get 1x on the right. Subtracting the 12, I get 21 on the, yep, there we go. Plugging this in just to double check. In my picture, I get this is 23. And then plugging it up here, 21 times 5 thirds. So 5 thirds times 21, well, that's over 1. That cancels. We get 7 and 1. So this is 35 plus 11. That's 46. And sure enough, it turned out to be twice as long, which is what we expected. Okay, now let's do this other one over here. I'll draw a little wall here. All right, so this one is saying, well, if we have a bunch of parallel lines cut, that means these are, wait, I mean, this isn't even a question. Like it's literally telling you those are equal. But anyways, if you have a bunch of parallel lines, that was our additional theorem here that said a bunch of parallel lines, cut it so that all these are proportional. So this ratio is equal to this ratio is equal to this ratio, or this ratio is equal to this ratio, right? So it cuts both of the transversals proportionally when you have parallel lines. And it makes sense, right? If you have a big gap here and a small gap here, those parallel lines aren't getting closer or further apart. You're going to have a big gap here and a small gap here, right? Because the parallel lines right here were closer and the parallel lines here were further. That's the idea, is parallel lines stay the same distance apart. So you essentially, yeah, I won't get into it. Okay. All right, so let's do that problem here. So we just know that this ratio is the same as this ratio, but it was already a 1-to-1 ratio. I mean, this isn't even a problem. I just wanted to show you what they were asking, but really, it just tells you these are equal, and it tells you these are equal. So you just go 2x plus 3 equals 6 minus x, and then over here you go 4y, or 4/3 y, plus 1 equals 2y. That was a silly problem, so I'll leave it. Then it's just algebra after that. All right, so here's a good one. This is when you have to put it all together. Whew! So look at this. We got triangle proportionality. We got 4 parallel lines cutting segments proportionally. So I'm going to start with 4 parallel lines, okay? So I'm going to say, well, this ratio is the same as this ratio. Okay, so up top, f is to 12 as 10 is to 15. Well, 10 is to 15 is just 2/3. Okay, so f over 12 is equal to 2/3. So multiplying by 12 on both sides, I get f equals 2/3 of 12, which is 1, that's 8. Okay, so f is 8. All right, I got that one. All right, and then we know that, oh, look at this. We know, I'm going to switch colors. We know that this ratio is the same as this ratio. Okay, so over here, so e is to 12 as 5 is to 15. So again, 5 to 15 is just 1/3. So e is to 12 as 1 is to 3. I don't know, let's cross multiply this time. Why not? And then divide by 3, so e is 4. Okay, so we go back over there. So e is 4. Okay, we got one more like that. So b here, and I'm just going to use these segments. Again, but it's because we have parallel lines. So I know, and I don't know, let's do in purple now. So b is to 5 as 12.5 is to 4. And you might say, decimal, no. Let's just multiply by 2 on top and bottom. So that's really 25 over 8. Okay, so now let's cross multiply. We get 8b equals 125. So b equals 125 eighths. Great. Okay, who cares? We're just going to put that in there. Okay, so b is 125 eighths, which you could figure out as, what, 15 point something. Oh, well. So we got 125 eighths there for that one. Now we need to find d. Now this is where we start hitting that common mistake, right? So for d, we have this triangle, 8, 10, d, is similar to the next bigger triangle, which is a total side length of 8 plus 12 is 20, right? I'm doing this triangle here. So 8 plus 12 is 20, and then 10 plus 15 on the bottom is 25. And the diagonal length there is 12.5. That's what we have. So my ratio I'm setting up is d is to 12.5, right? From this triangle to this one. That's the same ratio as, I don't know, let's say 10 to 25. But we could have used 8 to 20, same thing. And so on the right, we divide by 5 and we get 2/5, right? Same thing if you use this ratio. Divide by 4 and we get 2/5, okay? All right, so we get d over 12.5 equals 2/5. Cross multiply, we get 5d equals 25. Divide by 5, and we get d is 5. Okay, so d is 5. Let's erase that, write that in there. D is 5. All right, so now we need to use that to get all the other ones, okay? So let's do c. All right, so c, I'm going to use that small triangle again because it was so easy. 8, 10, and 5 is similar to, and then we have to do the big triangle c. So if this is c, then the entire length here is 10, 25, 30 down here. Oh, that's nice. We could just use that right there. But we'll do the top one too. And then this is 24. Okay, so I'm going to say c is to 30 as, that's equal to 5 is to 10. So I'm going to reduce that to 1 over 2. So c is to 30 as 1 is to 2. So it's already 15, but I'm going to cross multiply 2c equals 30. So c is 15. All right, so we got c is 15 here. And then I'm going to use that same small triangle to solve for a. So we go, oh, and this huge thing where I'm looking for a, that's similar to that same triangle with 5, 8, and 10 down here in the middle. And that's because of parallel lines, right? Corresponding angles, corresponding angles. Okay, so the whole bottom, oof, it's no fun, right? It's 125/8 plus 20 plus 30. I don't want to deal with that one. And the top one is 24 plus 12.5, so it's 36.5. Just double check. That's 24.5, 28.5, 36.5. Yeah. Okay. So if I want to solve for a, then I'm going to go a is to 36.5 in the same ratio as 5 is to 8. And then you just got to solve. So 8a equals, yeesh. So this is 36.5 times 5, which is, what's that? That's 73 halves times 5. Okay. So that's 8a equals 350, 365 halves. Ooh, 365. And then we go divide by a. So divide by 8. So 8 is 365 over 16. Woo! That's crazy town. But the key there is to use similar triangles when you're trying to find the parallel sides themselves. Because sure, they cut these sides proportionally, but the actual parallel lines themselves are just part of similar triangles. So you actually have to use similar triangles to find those. And that's, again, that common mistake I wanted to highlight. All right, so the last problem we're doing here, last problem is, how do you find, so if you know this ratio of fronts of these houses, how do you find the backs? Well, look, it tells you right angles. So you know by corresponding angles are congruent that all of these lines are parallel. So you know it cuts the bottom ones into the same ratio as the top ones. So, for example, you know the ratio of u to m, right? This ratio is the same ratio as 20 is to 22 up here, right? That's the idea here. It cuts it proportionally. So the question then is, if the total frontage is 135.6 meters, then how much of it does each one get? Well, this is just that extended ratio. It's saying that all of these are some multiple, right? So if these are proportional in that ratio, that means this is some multiple of that. This is some multiple, so it's the same multiple. We just don't know what that multiple is, right? So it's all of those same ratios from the top multiplied by some scale factor. That's the idea of what it means to be proportional. So the question is, if we add these up, 20 plus 22 plus 25, well, not m, plus 18 plus 28x, that's equal to 135.6. So we just got to find what's that scale factor multiple. So if we add all these up, let's see, this one and this one add to 50. So 50x plus 45x plus 18. That's 95x plus 18. That's 105 plus 8. So that's 113x equals 135.6. So then x, the scale factor is it got multiplied by this. All right, so if it wants to know what is it, what is the lot frontage for each of the lots? Well, each of them, so the first one is, you got 20 times the scale factor. The second one is 22 times the scale factor. And then you just keep going. And each one is just its front times the scale factor, which is a little over 1. And then the next one, 18 times 135.6 over 113. And the last one is 28 times 135.6 over 113. So you can go ahead and punch those all into a calculator. But that's the big idea, is whatever ratio is on the top is the same ratio as the bottom. And so then we just say, Well, if we know it adds up to 135.6, how do we cut it into that extended ratio? And simply adding up like 20 parts plus 22 parts, dot, 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 dot. See, how much is each part? Oh, each part is 1 point something. There you go, right? So 20 times 1 point something. 22 times 1 point something. Woo! Hope you enjoyed that video. That was a breakneck speed, you guys. All right. Hope you enjoyed it.